Okay, so we've talked about in previous units delta H, enthalpy. We recently talked about delta S. Well, by the way, the deltas are change. Delta S is change in entropy. And then we'll connect those two items with now G, and we'll talk in terms of delta G, change in G. G is Gibbs free energy. And we can use, delta G can be used for a lot of things, and there's some things that you'll use it in physics, but what we're going to use it for is to make a prediction about the thermodynamically favorable reactions versus the non-thermodynamically favored reactions. And we're going to use a couple different equations. We've seen this sigma equation previously with H's and then also with S's, and I don't think we really need to revisit that as far as practice. You're going to do it the exact same way as we did before. There is standard values in tables in the back of your textbook. You could find them on Google, and you just have to put in the right numbers and make sure, if it's H2O solid, you write down the H2O solid number, not the H2O liquid or H2O gas number. And coefficients still play a part, and you can figure out the delta G for the reaction. We're also going to use this equation extensively in this unit, and this is a favorite of not just my tests, but also the AP test in May, where you can relate the G, the H, and the temperature and the S. So Gibbs energy, enthalpy, entropy, and temperature. Okay, so let's get started. So let's actually look at this equation. Let's write this out. And this is in your equation sheet, so you don't have to memorize this. And by the way, you shouldn't try to memorize this table either. But delta G, if we find that it's negative, that means it's always thermodynamically favorable. The word they use in this little table is spontaneous. Okay, so spontaneous would be the negative value. Spontaneous still is the negative value. Okay, so but we'll get further into that in a second here. So let me erase that. So let's look at maybe this situation, this first one here. Delta H is positive. We're going to put a value in there for positive. Yes, there would be a number connected with that, but we're going to leave this as just a delta H positive. Temperature is going to be in Kelvin, so there are no negative temperatures. In this case, delta S was a negative. So if you look at this aspect, let me change that color. If you look at this aspect of the math here, a negative times a negative is going to give you a positive. If you add that positive value to the delta H positive value, you are always going to get a delta G that's going to be positive. And if you get a delta G that's positive, that means the previous word that we used to like was non-spontaneous or spontaneous. Now we like not thermodynamically favored or thermodynamically favored. So this is not going to happen on its own. This would be like an example of this. Of course, this isn't a reaction, but I think you'll understand what I'm talking about. If you have a ball at the bottom of the hill, it will not spontaneously roll up the hill. You would have to continually supply this with energy for this to get up to the top of the hill. That is what we're talking about. So there are many reactions that take place, but you have to continually make them happen. So another one of these that would be in this category would be your cell phone battery. So you can use your cell phone battery. That's in these words, in these contexts, is a spontaneous reaction. And then if you plug your cell phone battery up, that's the non-spontaneous aspect. Okay, so let's look at one more of those before we move on. Let's look at the spontaneous one. So if you have a delta G, well, you want to figure out delta G, and you have a delta H that's negative, and you have a delta S that's positive, that is going to give you a negative value, and then you already have this negative value, so no matter what the numbers are, you're going to get a negative for delta G, and that's why it says that. Now there's a couple other scenarios here, and we'll address those scenarios in the next couple slides. Okay, so there's a definition of delta G. We just mentioned favored or not favored. We didn't mention zero, but this is going to be an important item here. So if you have something that you know that's in an equilibrium situation, so something that is melting or something that is boiling, that's an equilibrium situation. So the delta G in those cases are zero. And we have to make sure we're cognizant of remembering that. We've already gotten this, were introduced to that before. By the way, delta G negative means it's thermically favored, but that also doesn't mean you're visibly going to see the reaction occur. Like for instance, hydrogen gas plus oxygen gas making water in the atmosphere, wherever you're watching this, that should happen. That should be thermically favored, but it's not happening because you have to overcome the activation energy. By the way, it's not balanced, not a balanced chemical equation, but these might collide with each other, but not with sufficient energy. So we have to deal with that too. If you rearrange the equation where delta G is zero, you're going to get that. I don't know if you really need to kind of address that. You can kind of address it just putting a zero into that spot if you had to. Okay, and so we talked about this table before. There will be a few of you that will just try to memorize this table. I would prefer that you not do that. And let's maybe try to take a look at some of these. So, melting of ice. Why is it not always thermically favored? So, think about it. You go, oh yeah, ice melts all the time. But no, it doesn't melt all the time. If you would go in the middle of February and it's a number of days in a row that are extremely cold below the freezing point, that snow or that ice isn't going to melt. But let's take a look at it. So we have a solid and we have a liquid. So what do we know about that? So for a solid to become a liquid, that has to be endothermic. Endothermic means delta H positive. So that's something that you guys should remember or know from previous units. What else do we know? The disorder of the system, the randomness of the system is increasing because it's going from a solid to a liquid. So now we're going to plug those in and see what happens. We're going to put a positive in for delta H. Temperature is in Kelvin. It's always going to be a positive digit. And then delta S is positive. So what's going to happen here? Well, it depends what part of this equation is bigger, is more significant. If the T times delta S is larger than the delta H value, then the answer comes out to be negative. And when would that happen? If the temperature is high. Now, these are arbitrary words, high and low. They're going to be connected to different numbers depending on what the circumstances is. And we'll talk about that with a few of these, including this one. We will talk about that. So delta G is negative if the temperature is high. delta G would be positive if that part of the equation is bigger, if it has a more significant value. And when would that occur? When the temperature is low. So a low value for T times whatever that delta S is would not possibly be as large as the delta H value. And we know this is the case. So if you have ice, I've never been to Antarctica, but I'm sure there's areas of Antarctica where the temperatures remain below freezing. So if you have a low temperature, solid to liquid does not occur with this H2O going to solid to liquid. But if you would take a piece of ice out of your freezer and lay it on the desk, I bet there is a high enough temperature for that ice to melt. So it happens sometimes and it doesn't happen other times. When I say happen, it's not thermodynamically favored to happen all the time. So what is that temperature threshold? Well, I think you guys know it's 0 degrees Celsius, or 273 Kelvin. Okay, let's take a look at a couple scenarios. This is the end result of photosynthesis. So let's go put our equation in here. We don't need numbers. We have a positive delta H. We have 6 gases going to 6 gases. So it's not really about the gases, but we have 6 liquids going to 1 solid. So that's becoming more orderly, less disorderly. So when you look at this, it's always going to be a value of positive no matter what the temperatures are. So that means it never happens. Nope, that doesn't mean it never happens. It's not thermodynamically favored for it to happen. It needs an outside influence. And you guys have already had biology, and you know that there's this thing called the sun that helps this reaction along. More than helps that reaction along. Next one, delta G equals delta H minus T delta S. We have a positive value again for delta H. We have 2 gases going to 3 gases. That's becoming more disorderly, so that's positive. So in this case, this could be negative sometimes. When will it be negative? If the temperature is high. You can use words, you can use that sign. I think people would understand what you're talking about if you had done that. Okay, let's look at another one here. This case, delta H is negative, and we have aqueous ions going to a solid. That's becoming more orderly, less disorderly. So delta G could still be negative, but the temperature would have to be low this time. You want the delta H to kind of win out in this case, not the T delta S component. And let's give this one a shot. And I also have a little picture here, so maybe this is a little foreshadowing what's going to happen. De Beers, they've had a advertising campaign forever, no pun intended, forever, where they say a diamond is forever. And so are diamonds actually forever? Or will they go back to graphite? And I have a little thing at the bottom here that says false advertising. So I guess they're not forever, but let's figure out, are they forever or are they not forever? Okay, we have a negative for delta H. Diamonds are about as orderly as you can get. Graphite is less orderly, more disorderly, so that's a positive. So it looks like the delta G always is going to be negative, meaning that always diamonds will revert back to graphite. So diamonds are not forever. Now it turns out that this process, the kinetics of this is extremely slow, but it's happening. It's happening. So if for someone's lifetime, it could be as good as forever, but it's not forever. Okay, let's see what we got here. So which phase change, solid to liquid or liquid to gas, has the higher change in entropy? So now we're trying to solve for delta S. Well, we already have a prediction that whenever you're having gases involved, that's the most important item. So this should be our answer. Okay, but let's prove it mathematically. So we still have our equation, delta G equals delta H minus T delta S. Remember, phase changes are equilibrium, so 0. We can only do one of these at a time. Let's do heat of fusion. Fusion deals with solids and liquids, so 10.9 kilojoules per mole. Temperature will end up being in Kelvin if we add 273 to it. And then we're going to be solving for delta S. On this one over here, we still have the same delta G equals delta H minus T delta S. Delta G is still 0 because it's a phase change, but now we're going to be using these numbers instead. So we have 31.0 kilojoules per mole minus 80.1 plus 273 delta S. Now both of these we should predict they're both going to be positive because solid to liquid becomes more disorderly, liquid to gas is more disorderly. And are they? Yes. And by the way, the delta H is in kilojoules, but if you leave your delta S in kilojoules, you're going to get a really tiny answer. So traditionally people don't. They multiply it by 1,000 to get it into a joules. If you look in the back of the book in the tables where you have the delta H, the delta G, and the delta S columns, the S value column is going to be in joules and the other ones are going to be in kilojoules because of that. So I did my conversion for this and I converted it into joules. The Kelvin and the moles stay attached, and so that's my value for solid to liquid. And then when I did this for the other one, I got 87.8 joules per Kelvin mole, and that matched up with my prediction. 87.8 is more than 39.1, so liquid to gas does have more change in entropy. Here's our sigma equation for this time delta G. You guys can go in the back of the book and do this equation as easily as we did with the delta H sigma equation or the delta S sigma equation. Elementals also have values of 0, so keep that in mind in case you can't find one. Let's look at a couple multiple choice questions. Which of the following reactions is not thermodynamically favored at low temperatures, but becomes favored at high temperatures? So we still have our delta G equals delta H minus T delta S. So we want an answer that's sometimes negative and sometimes positive. Let's look at, you can do process elimination, you can do a lot of different things. I'm going to use the signs, and I've done this before, so I kind of know what to go with, but if you don't, you'd start with A. If you don't like A, go to B. If you don't like B, go to C. If you don't like C, hopefully D looks good, or something went wrong along the way. So that's a positive value for the delta H. Remember, temperature is in Kelvin, always a positive value. That's a positive. So if the temperature is high, it's going to be negative. If the temperature is low, it's going to be positive, because that part right there. Okay, so it is answer B. Similar kind of setup. Goes essentially to completion. Which of the following is a true statement about the thermodynamic favorability of this reaction? So what do we got here? We got a negative. So let's go delta G equals delta H minus T delta S. We got a negative for delta H. We have a half a gas going to no gas. That's becoming more orderly, less disorderly. So we have that going on. I don't even know if we need all of that, but it looks like that you could have a negative or a positive. Let's see here. If you had a low temperature, you would get thermodynamically favorability there, or the other way around. Whoops. High temperatures, you get that to happen. Looks like we already have the answer. Let's try to figure out why we like A. Reaction is favorable and driven by the enthalpy. So the answer says it's driven by that, which is the case. That's the only way you can get negative, because this times this gives you a positive value, right? So it can't be driven by the T delta S portion. It has to be driven by the delta H portion. So I guess mathematically it's you can kind of think about it, it's driven like that. Okay, we have a reaction here, and we have a pathway. Looks like we have a path 1, path 2. Whenever you see these humps changing, this definitely has to deal with a, I'll just write catalyst up here. And the catalyst was actually going to be why that path 2 is lower. What else we got going on here? Plateau starts here and ends there. The difference of those two plateaus is 50 kilojoules per mole. So I have a feeling that we're going to probably need some of that to answer some of these questions. Like always, we've got the answers already. D, B, C. Let's figure out what's the most likely accounts for the difference between the reaction path. I had already mentioned that. Difference of these paths is a catalyst, and I said the lower hump is the one that actually has the catalyst, so I guess that gets us right to our answer already. We already talked about 50 kilojoules is the difference between the two plateaus. Plateau starts low, ends high, so that means it gained 50 kilojoules. That's an endothermic process. So that means the system absorbed energy. That means the surroundings lost energy. So that's basically what B says. Let's see. Reaction thermodynamically favorable under standard conditions at 298. Therefore, delta S is. So let's go back to do our delta G equals delta H minus T delta S. Thermodynamically favorable, we know that has to be a negative. This is 50 kilojoules absorbed, so that's a positive. Yes, we have a 298 in here. I guess we could put that in, but we could have just put T in there. And we're going to try to figure out what delta S would have to be. So what we really need to know is kind of who wins. Does the delta H make the delta G negative, or is it the rest of this makes it that way? And I think it would have to be this. So this means this has to be greater than that. And that's how they got that answer of C.